Hello viewers, welcome to Physics with Sanmitra. I am Sanmitra Bhomik, and in this series of last moment revision, today we are going to solve electrostatics MCQ, and the MCQs are chosen such that it will cover almost all of the syllabus. It will touch all the aspects of the electrostatics, and this series is highly useful for JEE Mains and NEET. JEE Mains and NEET aspirants, because the exams are almost there. Less than 1 month is left, so they should watch this very carefully, and they should practice this question so that they will be able to do well in the exam. Okay, let's begin. See, we have been given a square shaped arrangement where the charges are kept at the corners of this square, and now there are points like A, B, C, P and Q as shown. Now potential will be 0 at the points, and we have to find that these are the options. Okay, let's examine each of the point. Let's see. Here the point A is there, and can you tell me here that this point A, the potential depends on which charges? All the charges. Okay, let's see. Charge by charge. Let's consider the pair of charges. Let's consider these two as pair. I will tell you why. This one and this one as a pair, and with red I am showing these two as the other pair with orange. Now let's see, this distance and this distance, these are equal, and for plus q and minus q. So for these two charges, my net potential at A is 0, and for these two charges, this plus q and minus q, the net potential at this point A, that is 0, because this distance are same, and we know that potential formula is V is equal to kq by r, where k is 1 by 4 pi epsilon. And see this R, if this r is same, then I can say V is proportional to q only. So if I add them, it's a scalar quantity we can add. Plus q and minus q gives 0, and this plus q and minus q will give 0 because these two are distances are same and these two are same. So for A, my potential is 0. So A is there in option A, B and C. So option D is eliminated because A is not there. Let's look at P. Okay, now let's look at P. See, from point P, let's take these two charges. These two are on a negative charge, so they will have a negative potential contribution over here, over point P, and these two are positive charges. These will have positive potential at P. This contribution will be positive. Now these two distances are not equal, so definitely this will not cancel each other, so there will be some net potential here P. So P at point P, Vp is not equal to 0. So we can see here, we'll eliminate the options which are having P and here and P. So this first already eliminated. So my correct option, there is only one option left, that is C. B. Let's look at B and C. See, for option B, this point we have to examine. It is equidistant from all the charges, and this is plus q and minus q, plus q and minus q. So there are two pairs of charges, and the potential is 0 here. And also this point C, that is similar to point A, that is these two charges are having same distance, and this pair of charge, these two charges are having same distance from C. So I can say my correct option is option B, that is A, B and C. The electric field in the cavity we have to find. Here there is a non-conducting charged material, and one more thing that should be mentioned, that is, I'm mentioning it now, that is uniformly charged material. This is uniformly charged, and there is a cavity here. We have to find out the electric field in the cavity, and the options are given: 0 everywhere, non-uniform and non-zero and uniform, non-uniform, 0 only at the center of the cavity. Okay, now let's show you how to deal with this problem. First of all, this cavity, let me show you this cavity. This is the electric. Let's show you. This is my, I can say, sphere, and this has a cavity inside. Now this is charged, but this cavity has no charge. I will break it down in like this. I will assume that there is a complete sphere of, say, total charge. Let's say the charge density is rho, that is charge per unit volume. This is plus rho, and we'll take another smaller sphere. This will be having charge density minus rho. So if I superimpose them, I will get here, and this part, this actually what I am doing here is that here the charge density is 0. This 0 I am resolving into plus rho and minus rho. 0 is equal to plus rho minus rho, that I am doing. Now see, exactly I have done this here, and electric field inside a uniformly charged conductor, that is given in uniformly charged non-conducting material, that is given by rho is equal to, electric field is equal to rho into r vector by 3 epsilon naught. See, rho into r vector, why I am writing rho into r vector here? Because let me show you this. This is my uniformly charged, this is my uniformly charged conductor, not conductor, material. Now at a distance r vector, this is my r vector, the electric field will be rho r vector by 3 epsilon naught. We can derive it by Gauss law. We can derive this by Gauss law. We'll take the charge Q enclosed. Q enclosed will be rho into 4 by 3 pi r cube. 4 by 3 pi r cube. Now E dot ds, E into 2 pi r square is equal to rho into 4 by 3 pi r cube by epsilon naught. So actually it will be 4 pi r square. So if I cancel out this 4 pi and this 4 pi and this r square with r, I will be left with rho r by 3 epsilon naught. Exactly that what I have done here. E is equal to rho r vector by 3 epsilon naught. I have written in vector form. So I have just resolved this zero charge into plus rho and minus rho here. This part, if I superimpose, I will get this. Now let's see here. Let's take a point inside the cavity. Then electric field due to this sphere, that will go outwards. See, it is going outward here. And electric field due to the smaller negative sphere, that will go inward. So this is OP vector and O. Now the net electric field will be something like this. Now see, wherever I am keeping the point, the net electric field will be from O to O dash. So I can say the net electric field, okay, let me show you mathematically. This is rho, this is E1 plus E2 vector. What is E1 vector? Rho into rho by 3 epsilon naught, and the R vector, that is OP vector. And this one is PO dash vector, that is rho by 3 epsilon naught into PO dash vector is equal to rho by 3 epsilon naught OP plus PO dash vector. And this OP vector plus PO dash vector will give me O dash vector, simple vector algebra. So from this expression we can conclude that the electric field is the electric field has, you can say, same magnitude and same direction. See, this is a constant vector, I can say, and same direction also, since so I can say it is non-zero, it's not zero, and it's uniform because this is having a finite charge, and this cavity is situated at a farther distance, so O dash won't be 0 and rho is not 0, so it is non-zero. Okay, next question is, two parallel plate condensers of 20 microfarad and 30 microfarad are charged to the potentials of 30 volt and 20 volt respectively. If likely charged plates are connected together, then the common potential difference will be. See, there are two parallel plate condenser. Condenser means capacitor, another name for capacitor, that is having 20 microfarad and 30 microfarad, the capacitances. They are charged to potentials of 30 volt and 20 volt respectively. See, 20 microfarad is charged to 30 volt and 30 microfarad is charged to 20 volt. Now the likely charged plates, that means the positive with positive, I can say, and or negative with negative, are connected together, then the common potential difference will be. Okay, see, this was my case earlier. This is a 20 microfarad capacitor that is being charged to a voltage of with to a potential difference of 30 volt, and this is my 30 microfarad capacitor that is being charged to a potential difference of 20 volt. Now these are the plus these are my plus charges, I mean positive plates, and these are my negative plates. Now what will I do here? I will switch this off. Now what will happen? These two are in parallel connection. Now since these are in parallel connection, or actually the potentials of these plates were different, but when I'm connecting with a conducting wire, the potential will become same. All these will become equipotential surface, so the net voltage difference, I mean, that will be common. The common voltage will appear between these two, and therefore what I can say here is that, see here, common voltage will appear. Now let me apply charge conservation. Now why charge conservation? See, these upper two plates, these two plates, this now, and here in this case, these two plates, these were isolated. These two plates, if I consider together, these were an isolated system now, and now also these are isolated system, only they are connected. These two plates as a system, that is isolated as a system, both together if I consider. So if it is having 20 microfarad and 30 microfarad charge into 20 microfarad into 30, that is initially this charge, let's say plus Q1 and plus Q2. If this is having plus Q1 and plus Q2 charge, so this whole arrangement will have plus Q1 plus Q2 charge. The distribution may be different, but the charge will remain same. So I'm applying here charge conservation. Q1 plus Q2 is Q1 dash plus Q2 dash. This Q1 dash and Q2 dash are the new distributions. See, Q1 is C1 into V1, Q2 is C2 into V2 is equal to C1 V plus C2 V. That V I will get C1 V1 plus C2 V2 by C1 plus C2, where C1 V1 is 20 into 30, C2 V2 is 30 into 20, divided by C1 plus C2, that is 20 into 30, is equal to 24 volt. So my correct option is option C, that is 24 volt. Okay, moving on to the next question. There is a configuration here given, and let me make a small correction. This will not be D, this is a printing mistake, this will be A. Okay, now this configuration is given that all the charges are at a distance A. This is at a distance A, this is at a distance A, this is at a distance A, this is at a distance A. All the charges are at a distance A. Now dipole moment of this configuration. This is a bit tricky question, but I am showing you how to find the dipole moment. See, dipole moment is defined for there is a negative charge and there is a positive charge, and the distance between them, if I say that is say A, L, then dipole moment will be a vector that is defined. Dipole moment will be a vector defined from negative to the positive, this direction, and this is P vector, that is Q into L vector. Q into L vector. So what our job will be to find the dipole pairs in this one. Let's see this 3Q. If I can see, here is Q, so if I can make a dipole here, how will I make it? This 3Q, I can make one minus Q here. So if I make minus Q, then it should be 4Q remaining. 4Q minus 3Q, that is minus Q. This 4Q, I can take 2Q and 2Q to balance these two. 2Q will balance 2Q, 2Q will balance 2Q, pair 2Q will pair 2Q, minus 2Q, 2Q will pair minus 2Q, and minus Q will pair Q. So simply I can write here, I can resolve this 3Q into 2Q, 2Q and minus Q. See, this is distance is A, this is A, this is A, this is A, so this will be A root 2, and this is minus Q and this is Q. So I can say we are forming here 3 dipole. This is one dipole, this is the other dipole, this is the third dipole, and this dipole and this dipole, these two are having same value. This dipole and this dipole will have same value because they are symmetrical. This is minus Q, see 2Q and 2Q. So this one, I say this dipole is shown as P1, and this one will also be shown as P1 because they are symmetrical. This one, see, minus to plus, it will go downwards. This is P2. So what is P1? P1 I can say here minus 2Q into 2Q, minus 2Q into A root 2, or 2Q into A root 2 if I just show the magnitude. charge into distance between the two particles. Now what about P2? This is also minus q into q, that is 2a. So distance, so q into 2a. Now if I resolve this P1 into two components, this will be my P1 sine 45, this will be my P1 sine 45. P1 sine 45, this is my P1 sine 45, and this will be my P1 cos 45, P1 cos 45. I will together add them, they are in the same direction. 2P1 cos 45. So 2P1 cos 45 degree minus P2. See, P2 is in the downward direction, 2P1 cos 45 in the upward direction. So I will replace here 2P1 cos 45 degree, 2Q into a root 2 into 2 into cos 45 is 1 by root 2 minus Q into 2a. So 4QA minus 2QA, that is 2QA in the upward direction. So 2QA into J cap, this is X, Y direction. So option A is my correct answer. Moving on to the next problem. This is an electric field is given as y I cap plus x j cap Newton coulomb and the Newton per coulomb, and work done in moving a 1 coulomb charge from RA vector, that is 2 I cap plus 2 j cap meter, to RB vector 4 I cap plus j cap meter. We have to find the work done. Now just see here, we have been given an electric field that is a function of y and x, and we have to find the work done moving a charge from certain position to certain position, and the charge is 1 coulomb. Now how to find the work done? See, due to the I can say charge and due to the electric field on this charge, there will be a force, that is F in is equal to QE vector. Now if I find out work done will be integration of F dot dr. Since Q is 1, so I can find integration of E dot dr because Q is 1. So E vector is this one, and dV vector potential I am doing by potential. You can do by just work done also. I will just put W is equal to minus U, that is potential energy. So E dot dr, that is y I cap plus x j cap dot dx I cap plus dy j cap. See, y dx plus x dy, it will form like this. See, y dx plus x dy, what is this? D of xy. This is the standard result. So now d of xy, now I can say this has become a complete differential. Now we don't have to worry about two variables. Now the first RA vector was 2 comma 2 in Cartesian coordinates. We can write RB vector is 4 comma 1. So integration of v will be integration of dv is equal to minus of integration of d of xy 2 comma 2 to 4 comma 1. So this is xy 2 comma 2 to 4 comma 1. I can write, see, 4 comma 1 is 4 into 1, 2 comma 2 is 2 into 2, that will become 0. So my work done is 0. So work done is 0. Capacity of a spherical capacitor is C1 when inner sphere is charged and outer sphere is earthed, and C2 when inner sphere is earthed and outer sphere is charged. Then C1 by C2 is Ri is the radius of inner sphere, Rho is the radius of outer sphere. Okay, let's see what exactly they want to tell us. First of all, we have an inner sphere and we have an outer sphere. Let's draw it properly. This is one. Let's draw the other one also. Now in this case, let's take the inner radius as A. Let's take the inner radius as A, and let's take the outer radius as B. Here also let's take inner radius as A and outer as B. In the first case, what they have done is that they have earthed the inner sphere and outer is given a charge Q. In the second, what they have done, they have taken a charge Q here and they have earthed the outer. I think opposite. This is my C1 and this is my C2. Now what is my C1 and C2? C1 will be here 2 pi according to formula AB by B minus A. Here it will be C2 will be 2 pi, there will be an epsilon also, 2 pi epsilon B square divided by B minus A. So if I find C1 by C2, it will be A by B. So here the same thing it is done, Ri naught by Ro, Ri Ro divided by Ro minus Ri, and C2 is 2 pi Ro square by Ro minus Ri. If I take C1 by C2 ratio, it will be Ri by Ro. So my option B is correct. So you have to know the formula of the spherical capacitor, then you can do it quickly, else you have to derive. Two concentric spherical conducting shells of radii r and 2r carry charges q and 2q respectively. Change in electric potential on the outer shell when both are connected by a conducting wire, and k is given as 1 by 4 pi epsilon. Option A is 0, 3kq by 2r, kq by r, 2kq by r. Let's see here what is the scenario. There are two conducting spheres, and here q is there and 2q is there. And if I also consider the charge distribution, due to this q, here minus q will be induced, and this due to charge conservation, here this 2q, this will be 3q. So this is my, even after charge conservation, this is my configuration. Now what I will do, I will connect these two. Now when I am connecting these two, what is happening? The potentials become equal. And also one more property which we will be using, then it will be easier. Charges move. Let me say it actually. Charges move outwards. Charges move outwards. That means this q charge will be moving to the outer shell when in a metal or in a conductor, the charges will move to the outermost surface. This is the property of a metal, and this thing I have already covered in a video. So if you want to see it, you can, there is the link in the comment section, you can find it out. That is the why charges move outside the conductor, move towards the surface of the conductor. Okay, now see, I have connected here this, and this q charge which was here, it has moved out to the outside and it has become 2q plus q. So now the net charge on the outer surface is 3q, and let's see what we were asked to find. The potential on the outer shell. Potential on the outer shell will be k into 3q by this radius, that is 2r. K 3q by 2r. That is the potential on the outer shell. So my correct option is 3kq by 2r. That is option B. Now these are the area of each plate. We have some plates here. There are 4 plates. Area of each plate is A. The distance between them, that means this distance, that is D. Then find the equivalent capacitance between A and B, that is written as CAB. Okay. Now let's see here. While doing this type of problems, I will be doing one thing. I will be naming the plates. That means the inner side of the plates I will start. Let's say this is 1, this is 2, this is 3, this side is 3, this is 4, this one is 5, and this is 6. I will not name these two. I am not naming this outer surface because they are not contributing to capacitance. That means they are not facing any other plate. Okay, so I have already named them, and you can see here 1, 2, 3, 4, 5, 6. See, the individual plate surfaces, I will consider them as separate plates. I'll show you why. The individual plate surfaces, I will separate them as consider them as separate plates. See, this 1, 4 and 5. This 1, 4 and 5 are connected to A. So therefore I will draw 3 plates, 1, 4 and 5. I will name them and I will connect them to A. And just opposite to 1, what is the 2? I will connect just opposite to 1, I will write 2 here. This 2 forms a capacitance pair. Now this opposite to 3, 4, I will get 3. So opposite to 4 I have drawn 3 here. Then opposite to 5 I will draw 6 here. Okay. Then 2 and 3 they are same, and 6. All 3 are connected to B. So 2, 3 and 6 are connected to B, and this is C and C. There are the capacitances and they are in parallel. So if one capacitor I can say for one, it is epsilon naught A by D. So if there are three capacitors C and C, that will be 3 epsilon naught A by D. So my option B is correct. Option B is correct. So this is a unique method of solving this kind of questions, and now I think you can visualize that these three are in parallel. Before that it was difficult to visualize. A conducting shell of radius r carries charge minus q. A point charge q is placed at the center. The electric field varies with the distance r from the center of the shell. See, we're asked to plot the electric field. So okay, let's solve this question. This is my conducting sphere. This is given a charge minus q. At the center of the conducting sphere, I am keeping a charge plus q. Due to this plus q, there will be an equal and opposite induced charge at the inner surface. All these things I have already explained in another video. I have already told you that is why charges move outside the outside of a conductor towards the surface. Okay, this is minus q and this will be plus q will be induced. So at the outer surface my net charge becomes 0. So all the minus q charge will be attracted inside. Now let me draw the Gaussian surface. Inside the conductor for say this R. Now q enclosed inside, that is q simply. So I can write here that E into 4 pi r square is equal to q by epsilon naught, or simply that is the result of Coulomb's law only. I will be getting 1 by 4 pi epsilon naught r square. This is for inside. Now let's see for outside what happens. See, for outside, if I see like this, for outside, inside there is plus q and also here is minus q. So if I draw a Gaussian surface, here, then it will enclose 0 charge. Since q enclosed is 0, I can say my electric field is also 0. So you can see this, the closest option that matches is this one. Inside it is varying as 1 by r square and outside it is 0. So option A is correct. And my next question is, here 3 capacitors are connected in parallel, so it is 3C I can assume, and this is, I can say this equivalent is 3C, and there is a switch like this. Initially it was charged, and after on closing the key, this key is being closed, then the charge flowing through the cell on closing the key. Okay, how to do that? Initially, let's see, initially how was the configuration? This is 3C, this is 3C, this is C, and this is the battery. This is V, this is C, this is 3C. Now what is the equivalent capacitance? 3C into C, they're in series. So I can write here 3C into C by 3C plus C. So the equivalent capacitance is 3C by 4, and the charge is 3C by 4 into V, that is 3C V by 4. Charge on each capacitor is 3C V by 4. Now what is happening? Even here also the charge is 3C V by 4. Now what is happening here? When I am short-circuiting this path, then the net capacitance becomes C. So my initial, I can say here that my initial charge Q1 on this 3C plate, this 3C plate, I can say that is 3C V by 4. Now then finally it becomes, the capacitance becomes, this becomes short circuited, capacitance becomes C. So now the charge is CV. Q2, who is supplying this extra charge? Extra charge is supplied by the battery. So when the extra charge is supplied by the battery, then it is, I can say this, that is del Q. Del Q is Q2 minus Q1. CV minus 3 CV by 4, that is CV by 4. So when the switch is closed, then the charge that is flowing through the key, that is CV by 4. Moving on to the next question. Two capacitors are in series which are geometrically identical. See, these are the capacitors and these are in series and geometrically identical. With dielectric, this when the dielectric is given and the dielectric constant is, this is not mentioned, let me write it as K. The dielectric constant is K. The charge on capacitor, this Q1, this is my capacitor 1. This is my capacitor 1 and the charge here is Q1 and the charge here on this capacitor 2 is Q2. 1 and 2 is Q1 and Q2. And when the dielectric is removed, now this battery is kept connected and I am removing the dielectric. Now what the charge is Q1 dash and Q2 dash. Now we have to find Q1 dash and we have to verify Q1 dash by Q1 is K plus 1 by K, option A. Option B is Q2 dash by Q2 is K plus 1 by 2. Option C is Q2 dash by Q2 is K plus 1 by 2K, and D is Q1 dash by Q1 is K by 2. Okay, now let's see here how to approach this problem. First of all, these two are in series. So in series connection, let me say this is the capacitance is C for this air capacitor, and this is also C, but there is a dielectric here. There is a dielectric here and due to the presence of this dielectric it will become K times C. So now what I can write here is that the equivalent capacitance, that is C into K into C, that is a series combination, C into K times C divided by C plus KC. So it will come out to be K into C by K plus 1. So, and now the charge will be same. This is plus Q, this is minus Q, this will be plus Q, and this is minus Q because they are in series. And this will be, that means Q1 will be equal to Q2. Q1 will be equal to Q2. So let us look here. C equivalent we have found out, and Q1, that is K by K1 plus 1 into C, that is my C equivalent into E. So that is my Q1. So what is C equivalent dash? Now when I am removing the dielectric, that time the C equivalent dash will become only C and C in series, that will be C by 2. So Q1 dash will be C by 2 into E. Now Q1 dash by Q1, let me find. There are options C, Q1 dash by Q1 and Q2 dash by Q2. Although Q1 dash and Q2 dash are same, Q1 will be equal to Q2, Q1 dash will be equal to Q2 dash. Okay, so Q1 dash by Q1, so Q1 dash here and Q1 here. So if I can write it, the ratio will come K plus 1 by 2K. Now I can say one thing, this is the same thing will be Q2 dash by Q2. So my answer is here Q2 dash by Q2 is K plus 1 by 2K. So option C is the correct answer. Now, a charged particle Q is shot from a large distance with a speed v towards a fixed charge Q. See, here is a fixed charge Q and here is a fixed charge Q, and a large charged particle is being shot here, and there is a repulsive force acting between these two. Now it approaches Q up to a closest distance r. It approaches Q up to it will go, imagine this pointer is this charged particle, it will go towards Q, the velocity will start decreasing and that will be converted into the potential energy, and up to a closest distance r, and further it cannot go, and then it starts moving and then it returns. If Q were given a speed 2v, the closest distance of approach would be, okay. Now this kinetic energy of this particle that is being converted into potential energy. So we can write kq into q by r is equal to half mv square. See, k, q, q and 2m, all these are constant, so only r and v are variables, so rv square is equal to constant. So let me compare. R2 v2 square is equal to r1 v1 square. R2 will be equal to r1 into v1 by v2, that is v1 by v2 whole square. Since v1 is v and v2 is 2v, I can write here this v1 is v and v2 is written only 2v. So this is 1 by 2 whole square 1 by 4, so r2 will be r by 4. So it is r by 4 is my correct answer. That means if the velocity was 2v, the distance of closest approach would have been reduced by 4 times. A wheel having mass m and charge q and minus q, diametrically opposite points. See, this is the wheel and here it is a charge q and here is a charge minus q. It remains in equilibrium over a rough inclined plane in the presence of an uniform vertical electric field E given by. Now to find the value of E, and this is a uniform vertical electric field and it is in equilibrium. So if it is in equilibrium, let me analyze the forces. This is Q, so this will be my QE vertically upward, and this is minus Q, so this will be my in my minus direction. This is minus QE. Now what I can write here is that, and this is mg downwards. Mg is downwards. Now it is in equilibrium, and also there is a normal reaction, normal force. This normal force would act like this. Now how can I balance this? So along this normal force there is nothing, but along the perpendicular, let me see, this is mg sine theta. This is mg sine theta, and this, due to this QE, I can say this is angle theta, so this will be this angle theta, this one. So QE cos theta, and since this QE is on the downward side, so I can also say QE cos theta on this side, QE cos theta. Now let me do one thing. Let me balance torque. Let me balance torque around about this point. So I can eliminate two forces here. This N, because it is touching here, and this QE. So if I balance torque, I will get QE cos theta, QV cos theta into 2r. This will have torque in this direction is equal to mg sin theta into r, and this will have a torque in the clockwise direction. This will have a torque in the clockwise direction. So if I solve this, I will be getting E is equal to mg tan theta by 2q. So my correct option is option C. Moving on to the next question. The dipole moment of a system of charge q plus q, of a system of charge q that is distributed uniformly on an arc of radius r, subtending an angle of pi by 2 at its center, where another charge minus q is placed. So what is the dipole moment of the system? Let me analyze this at first. Let me show you, then I will show you the calculation. This is the arc and this is the center, and the charge is, let me take, this is my center line, and this is pi by 4, this is pi by 4. Now let's take an elemental charge, that is dq, and let's take an angle here, that is d theta. The angle being here d theta, and here the angle is theta, and due to, and see here minus q charge is there, minus q charge is there here. For let's take a dq charge here, and from this minus q only, let's take some minus q dq charge out here from this q. So this minus q and this dq, that will form a this will form a dipole. Let's say this dipole moment is dp, and this is theta, so I can write dp is equal to dq is the charge and r is my distance. So this is my theta, so I can write the net dipole moment see this dp I can resolve into two components. One is dp cos theta upwards and dp sin theta this side. And here again, when I will be calculating dp here, this will be dp cos theta will upwards and dp sin theta will be this side. So dp sin theta will eventually cancel out. So my net force will, that will be net dipole moment that will be remaining. That is integration of dp cos theta. Integration of dp cos theta will be my net dipole moment. So exactly, let me find out here. I have already shown here in dp cos theta. What is dp? The dp is, say, dq into r. So what is dq? dq is for this angular, this length. What is the, see, for this total angle pi by 2, I can say the total charge is q. For this d theta angular displacement, then this is q divided by pi by 2 into d theta. So minus pi by 2 to pi by 2, q by pi by 2 into d theta into r cos theta. So 2q r by pi by 2 integration of 0 to pi by 4 cos theta d theta. So that will come out to my 2 root 2 qr by pi. So my correct answer is option A, 2 root 2 qr by pi. 4 concentric shells of A, B, C, D are given are of radii A, 2A, 3 and 4A respectively. Shell B and D are given charges Q and minus Q respectively. Shell C is now earthed. Find the potential difference. VA minus C is find the potential difference of VA minus VA minus VC. Okay, so we have 4 shells. This A, B, C, D of radius A, 2A, 3 and 4A respectively. Now this shell B, this B and this D, these are given charges Q and minus Q respectively. Now this for this shell C, for this C we are earthing this one. So what will happen when we earth this? When we earth this VC will become 0, but VC is not actually 0 here, because VC will have some value, finite value, because of this minus Q. This is VC is now, what is VC? VC is, let me calculate, before earthing, KQ by the total, that is 4A, KQ by 4A, and minus also because the minus charge, plus KQ by due to this one, that will be 3A. So definitely this is not 0. So there is the need of one more term that will make it 0. So that is why I can say that a charge will be induced, let that be Q dash. A charge will be induced from the ground. So plus KQ by 4A plus KQ by 3A plus KQ dash, there is the induced charge from the ground, by 3A is equal to 0. Now I can say it is 0. This Q dash will be such that this potential will be 0. See when it C dash is Q dash, so I will get Q dash is equal to, from this expression, minus Q by 4. Now if Q dash is minus Q by 4, so what is the potential of VA? See, we are asked to find VA minus VC, where VC is already 0. So it will be ultimately VA minus VC will be VA only. So VA is now KQ by 2A. VA is KQ by 2A minus K into Q by 4 by 3A minus K into Q by 4A. See, VA, what will be VA? VA will be due to this, due to B. B was having Q. If V was having Q, then it will be KQ by 2A, since the radius of B is Q. So inside, due to the component, the contribution due to this B, this Q charge, that will be KQ by 2A. Due to this one, there is minus Q by 4. It will be minus of K into Q by 4 by 3A. And due to the last charge, there is Q, and the radius is 4, and there is minus Q actually. So minus of KQ by 4A. So answer is KQ by 6A. So VA minus VC, that is VA, and VA minus VC will be same thing, KQ by 6A. Moving on to the next question. The space between plates of a parallel plate capacitor is filled with dielectric whose dielectric constant varies with distance as per the relation Kx is equal to K naught lambda x, where lambda is a constant, and C is equal to C naught for vacuum. Then these are the 4 options. We have to find the equivalent capacitance, and see here the dielectric constant is varying with the distance. Okay, so this is my capacitor, and this is the distance x, and I am taking an incremental length, that is dx. Now how to find the capacitance, that is the equivalent capacitance? See, for this much, see, this is actually series combination. So in series combination, what we can do is that we will write 1 by C, and that we will add but here we'll not add because this is a continuous variation, so we'll integrate. So let's see what we have done, what we can do here. So we can integrate this one. We can integrate c d epsilon naught a by d is c. So we are doing it in the opposite direction. So dx, that is this length, this is the distance, epsilon naught a by d, that d is here dx. So dx by epsilon naught a, and there is a dielectric also, that is k epsilon naught a by d. So that dielectric we can write here as k of is a function of x, that is 1 by c. We'll get the variable as final result as 1 by c. So this k is k naught plus lambda x. This is from 0 to d. Now we'll integrate it. We'll take taking lambda common. So epsilon naught a lambda, integration of 0 to d, that is dx by x plus k naught by lambda. So 1 by lambda a epsilon naught, that is integrating this one, I will get ln d plus k naught by lambda by k naught by lambda. So 1 by c is 1 by lambda a epsilon naught ln of lambda d by k naught plus 1. So c will be lambda a epsilon naught by ln lambda d k naught plus 1. Just we have to understand this part. This part if you understand, then this problem is just integration. See, epsilon naught a by d, that is my c naught. So I have to multiply d here, then I will be getting a d here. So lambda epsilon naught d by ln lambda d by k naught plus 1. So my correct option is option D. Option D is my correct option. See, this figure shows three circular arcs, each of radius r and total charge as indicated. The net electric potential at the center of curvature is. See, this part is having a net charge of minus 2q. This part is having a net charge of plus q, and this part is having the net charge of plus 3q. See, all the parts are having the radius same. So I can write it like this actually. This is very simple now. See, volt minus of plus of for this part, plus of kq by r, because everywhere it is same, so I will just add up. There is no significance of this 45 degree here. This minus of 2q, this total is 2q, so I will write here minus of k into 2q by r, this r is same, plus k into 3q by r. So 3q minus 2q, that is q plus q, that is 2q. So 2kq by r, I have done it already, 2kq by r. So this k I will replace by 4 pi epsilon naught, then 2 by 4, this will cancel out, this will cancel. So q by 2 epsilon naught, 2 pi epsilon naught r. So my option A is correct. A parallel plate air capacitor is charged to a potential difference of V volts. After disconnecting the charging battery, the distance between the plates of the capacitor is increased using an insulating handle. As a result, which potential difference of the plates does not change, becomes 0, increases, decreases. Just see here what is exactly happening. At first, it is connected to a battery. Then what is happening? It is connected to a battery. Then there is a charge that is induced. Now a battery is removed, but the charge still remains. Now as soon as the battery was there is a constant potential difference, but as the battery is removed, the voltage may change. Now what is it is done by the insulating handle. Insulating means there is no leakage of charge. This distance is being increased. Now since this distance is being increased, then what is happening? See, this charge is constant. So now what will happen to the potential? That I have to see now. See, electric field, that is actually constant. Since electric field is constant because the charge density is constant and charge density is constant, therefore I can say electric field is equal to sigma by epsilon naught. So since sigma is constant, this E is constant. If E is constant, if D is increasing, V also has to increase. So the potential actually increases. Now I think this much is clear. A fully charged capacitor as a capacitance C. It is discharged through a small coil of resistance wire embedded in a thermally insulated block of specific heat capacity S and mass M. If the temperature of the block is raised by del T, the potential difference across the capacitance is. Let's see, this is a very interesting question. They have combined the concepts. This is a capacitor and it is passing through a coil. This is a resistive coil, only resistance is there, and this coil is mounted in a, it is embedded in an insulated block and the specific heat is S. Now as the it is discharging, this energy is being released as heat, that is I squared R, I can say, and since this energy is released as heat, what I can say, it is used in raising the temperature. Then what I can actually write here, that is what is the total energy of the capacitor. The capacitor energy is, I can say, half CV square, that is being totally discharged in a RC circuit, and that is being used to, there is ms into del theta del T, that is used to raise the temperature. So V I can write that is 2 into m s del T by C. So option C is the correct answer. Two identical metal plates are given positive charge Q1 and Q2, where Q1 is greater than Q2 respectively. If they are now both are positive also, now brought close to each other to form a parallel plate capacitor with capacitance C, what is the potential difference between them? See, let me draw the two plates. These are the plates. They are given charge Q1 and Q2. Let's assume at one side I am giving here Q and the other side I am giving here minus Q. Because the induced, it will become minus Q. If I give here Q, it will become minus 2 due to induction. Now this will become Q1 minus Q and this will become Q2 plus Q. Q1 minus Q and Q2 plus Q. Now if I can solve this on what I will get, I'm doing it directly. This is my plus, this is my plus. These two charge will be equal, so this one will be Q1 minus Q2 by 2, Q1 minus Q2 by 2, and the outside it will be Q1 plus Q2 by 2 and Q1 plus Q2 by 2. See, Q1 plus Q2 by 2 and Q1 minus Q2 by 2, and here it will be minus. So if I add these two, I will get here Q1, and if I add these two, I will get here Q2. So the potential, the inner charge, see the what forms the capacitance. Capacitance is formed by the inner charge, just inner ones. So since it is formed by the inner charge, so what I can say here is that my Q for the capacitance is equal to Q1 minus Q2 by 2, and Q is equal to CV. So the potential difference C will be Q by C. So Q1 minus Q2 by 2C. This is my answer. Next question. A positively charged particle is released from rest in an uniform electric field. The electric potential energy of the charge remains a constant because electric field is uniform, increases because the charge moves along the electric field, decreases because the charge moves along the electric field, decreases because the charge moves opposite to the electric field. First of all, I have an electric field and I have a positively charged particle. What will happen if I release it? Definitely it will move along the electric field due to a force, that is QE, that will be acting on it. Now now it is asked about the potential energy. Now what is electric E? E is minus of dV by dx. E is minus of dV by dx. So from high potential energy to low potential energy, that is electric field is flowing. So electric field is exists from high to low. So if I am leaving it, so it will move the electric potential, it will decrease because charge moves along the electric field. And just think in simple terms. I'm just releasing a charge in a conservative field. So what will happen? It will try to lose its potential energy. it will try to lose its potential energy, and it will try to reach a more stable state. Okay, so my option C is my correct answer. Option C is my correct answer. Now next question. Two thin wire rings having radius r are placed at a distance d apart with their axis coinciding. Let's draw the figure. This is one ring and this is other ring. There are two rings placed at a distance d apart with their axis coinciding. The potential difference between the centers of the two rings. Potential difference between the centers of the two rings. I think there should have been another option which I have not. It is not there. Let me see. First of all, the charges on the two rings are plus q and minus q. Let's say this is plus q, this is minus q. Let's say the potential difference at this one. This is, let me say, A, and this is, let me say, B. So at A, what will be the potential difference? See, this is the radius. If I can say radius is r. Now this one I can say root over of d square plus r square. So VA will be KQ by, due to this one, KQ by R minus KQ by root over of R square plus D square. This much is okay. Okay, that was about VA. Now what about VB? VB is my, due to this one I will get minus of KQ by R, and due to this one I will get plus of KQ by root over of R square plus D square. Okay, now I can see that VA is exactly opposite to VB in terms of sign. Magnitude is same but sign is exactly opposite. So VA minus VB will be twice of anything one of this. So I will get the answer as this one. See, because this one I can write this 4 2 into this. So you can solve it and you can find it out. This is option A. Now next one. Two spherical conductors of A and B of radii A and B are placed concentrically in air. These two are connected by a copper wire as shown. Then the equivalent capacitance of the system is. Now what will exactly happen here is that I am connecting both the conductors. So if I put any charge here, it will automatically come outside. Let's say I am putting a plus q charge here, it will automatically come outside. So effectively this is a single conductor. Now effectively it's a single conductor because I am connecting these two conductors with a conducting wire. So whatever charge I will give inside, it will come outside. I have already discussed this in one of my videos. So this is similar to another problem. So I can say it will be just 4 pi epsilon naught into B. That is the outer part. So it is effectively, this is the, I can say this is effectively it is a single spherical conductor with a radius B. A capacitor of 2 microfarad is charged as shown in the diagram. When the switch S is turned to position 2, the percentage of its stored energy dissipated is. So initially what is happening, here this voltage V is there, and this voltage, due to this voltage V, here it is applied over the capacitor, across the capacitor, and the 2 microfarad capacitor is now charged to voltage V. And in the next instant what is happening, this 2 microfarad capacitor that is connected directly across the 8 microfarad capacitor which was uncharged, and this 2 microfarad capacitor was charged, and since the 2 microfarad capacitor was charged, I can say that now they will be at a common potential. Now let's examine only these two plates. If I examine only these two plates, then final voltage I can say, we have already done a similar problem before, C1 V1 plus C2 V2, here it is 0, then I can write C1 plus C2 into V, and the loss in the dissipation formula, already there is a formula that is similar to the inelastic collision, perfect inelastic collision, that is del U, there is a loss in potential energy, that is half into C1 C2 divided by C1 plus C2 into V1 minus V2, or here I am writing V1 minus V2 whole square. Here V2 is 0 and V1 is V. Okay, so let me show you the solution. So initially it was like this, it was connected. Now when it is changed, what is happening here, this is the case. Now this will be there will be some V dash, there will be some V dash after charge redistribution, I can say. There will be some V dash voltage. Here it is 2 microfarad, here it is 8 microfarad. Here the voltage will be same because both the terminals are connected in parallel. Now, so the initial energy was half into 2 into V square microjoule, and the loss in energy is half into C1 C2 by C1 plus C2 into V1 minus V2 whole square. That is half into 2 into 8 by 2 plus 8 into V square. This formula you can derive by finding the final state energy, and if you subtract it with the initial energy, you will get this expression. This is very important expression. So half into 2 into 8 by 2 plus 8 into V square, that is half into 1.6 into V square. So delta U by U is 1.6 by 2 into 100%, that is 80%. Moving on to the next question. Identify the false statement. Inside a charged or neutral conductor, the electrostatic field is 0. The electrostatic field at the surface of the charged conductor must be tangential to the surface at any point. There is no net charge at any point inside the conductor. Electrostatic potential is constant through the volume of the conductor. Now just see here. This is a statement. We have to identify the false statement, and the statements are related to the properties of conductor. Now, let's see. Inside a charged, first point, inside a charged or neutral conductor, electrostatic field is 0. And yes, that is true, electrostatic field is 0. I have already made a video on this. You can watch it. And the electrostatic field at the surface of the charged conductor must be tangential to the surface at any point. Okay, let's keep it at hold. Let's look at the other options. There is no net charge at any point inside the conductor. There is no net charge at any point inside the conductor. Yes, that is true, because the charge tends to come out towards the surface. So there is no net charge. And also inside the, okay, I will tell you. And electrostatic potential is constant throughout the volume of the conductor. And the conducting material is equipotential. A conducting material is equipotential. Okay. So these three statements are correct. That is, I can say A, B, A, C and D are correct. So now left with B. So let's examine the surface of the conductor. This is the surface of the conductor, and let's take a if suppose let's take the electric field E as at some angle, and this is my theta. So if I can break it into components, this is my E sin theta and this is my E cos theta. Now just understand one thing. This component, what is, see, this is an electrostatic case. Electrostatic means there is no movement of charge. Now if I place an electron here, or if I place an electron here, since electrons are free to move in conductors, due to this E sin theta component, this electron will start moving in this direction, in the opposite direction. This electron will start moving in the opposite direction, I can say, in this direction. Now if the electron is moving in this direction, so there is a movement of the movement, so I can say it is, so there is a potential difference. Let's say this is plus, this is minus. There is a potential difference, therefore the electron is moving from minus to plus here. So but in electrostatic condition, the conductor will have same potential. Therefore, I have to say that this E sin theta will be 0 and theta will be 0. So there will be no tangential component. The work done due to this electric field should be 0 because there should be no potential difference. So only E cos theta remains. So the electric field is said must be tangential. That is fully wrong. It should be must be normal. This should be must be normal, and there should be no tangential component at all. Okay, so my correct answer is false statement is B. It should not be tangential. Now see, A, B, C, D, E, F. There are six plates. These are the conducting plates of area A, and any two consecutive plates are separated by a distance D. The net energy stored in the system after the switch S is closed. After the switch S is closed, the net energy stored in the system we have to find out. See, this type of question we have already solved in a previous question in this series only. So we will just number it. This is 1, 2. Let me show you. See, 1. There are 6 plates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The outer parts I am not writing because they are not facing anything. See, 1, 4, 5, 8, 9. These 5 plates are connected to this one, this terminal. 1, 4, 5, 8, 9. Okay. 1 is connected to 1 is opposite to 2, so I'm drawing here 2. 4 is opposite to 3, I'm drawing here 3. 5 is opposite to 6, I'm drawing here 6. 8 is opposite to 7, I'm drawing here 7. And 9 is opposite to 10, I'm drawing here 10. See, 2 and 3 are the same plates, so I'm connecting 2 plates and 2 and 3 with a wire. 6 and 7 are same. Here 6 and 7 are same. So I'm connecting 6 and 7 together. And just opposite to 9 there is 10. So opposite to 9 I'm getting at 10. But see one thing, these capacitors are actually not connected here. These two are, this is open, this part is open. So only one combination of capacitor is finally left out. See this one, only one. It is connected to A and this is connected to B. Now, so I can write here C is equal to epsilon naught A by D. So I can, the energy stored will be half into CV square. So what is, let me see the options. Half CV square, CV is half CV square, I can write. So half into C is epsilon naught A by D here. So I think option C is correct. Half into epsilon naught A by D into V square. So option C is correct. Let's look at this question, very interesting question. A parallel plate capacitor is made up of 2 plates of length L, width W and separated by a distance D. A dielectric slab, dielectric constant K, that fits exactly between the plates, it is held near the edge of the plate. It is being pulled away by the capacitor by a force minus del U by del X, where U is the energy of the capacitor, where dielectric is inside the capacitor up to a distance X. If the charge on the capacitor is Q, then the force on the dielectric when it is near the edges. Okay. Now let's visualize the thing at first, because this question many of you find it difficult to visualize. Otherwise this question has nothing to do, but the visualization is important. See, this is the plate of my capacitor and I will be drawing the dielectric. This is the part of the dielectric that is inside. Now this capacitor is connected to a battery. Let's say it's connected to plus V and this is earthed. Now see, there is a charge on the capacitor that is plus Q and here it is minus Q. This charge is uniformly distributed. Now due to this plus Q, there will be an induced charge, charge here. There is minus Q and there is induced, there is plus, some plus will be there. Now if you understand properly, due to this plus and minus, there will be some attraction like this. This will be due to the fringing field. This minus 2 plus, there will be some attraction. This is due to the let me tell you, fringe effect or fringe field. This is the fringe field effect. That means this field which is actually fringing out, that field, the component, the vertical component or this component will actually pull this block up, and that force we will find like this. We'll at first find the potential energy U. At first we'll find the U and then we'll differentiate with respect to X to find it out. See, this is my capacitor and it is inserted at a distance X distance and the total length is L. So this is X and this is L minus X. So epsilon C is equal to epsilon naught by D, and this area it will be, that is in air, that will be L minus X into W. What is W? W is this one actually. If I can draw like this is my W. So this is my L minus X and L minus X, and this is my W. So this area will be L minus X into W, and this will be, and in the dielectric this part, that will be X into W. This is X and this is W. So this is K into epsilon naught into D. So these two are in parallel, so I can add them up. And if I take epsilon naught W by D common, so it will be L minus X plus KX epsilon naught W by D, that is L plus X into K minus 1. U is equal to half CV square. Now what can I do here? I will differentiate this U. F is equal to minus del U by del X. So F this magnitude half V square into, it was half CV square, del C by del X. Now del C by del X, I will get epsilon naught W by D into K minus 1. So V squared by 2 epsilon naught W by D into K minus 1. Now see here, now what I can do here is that I can replace Q is equal to CV, and this C I will be writing here the epsilon naught A by D, and if I substitute it, I will get my correct answer as option C. The correct answer will be option C. And just see, this term does not depend on X. Doesn't depend on X. So if it doesn't depend on X, then I can say that the length it is inserted, that the fringing force will not depend on that. Okay. A surface has area vector A vector is equal to 2i cap plus 3j cap meter square. The flux of an electric field through it is, if the electric field is E is equal to, E vector is 4i cap meter volt per meter. So this is a fairly simple question, that is phi, I can say phi is equal to E dot A, simply. So this I cap dot I cap will be 1 and this I cap dot J cap will be 0. So my answer is very simple, 4 into 2, that is 8 volt per meter. Two small similar metal spheres A and B having charges 4q and minus 4q, when placed at a certain distance apart, exert an electric force F on each other. When another identical uncharged sphere C first touched with A and then with B and then removed to infinity, the force of interaction between A and B for the same separation will be. Let's see what this question is exactly demanding. This is Q, this is 4q, this is sphere, and this sphere is minus 4q. They are placed at some certain distance and they are exerting a force F on each other, and this F will be proportional to, F will be proportional to, I can say, 4q into 4q. Now I am taking a charged sphere and I am touching it. So after touching it, what will happen? After touching it, it is 4q plus 0. This is same everything. So 4q plus 0 by 2, that is 2q and 2q. Now I am removing this one from here and I am touching this sphere, the charged sphere of charge 2q with this minus 4q sphere. Now minus 4q plus 2q, that is minus 2q. This minus 2q charge, this net charge, will be distributed equally between these two, that is, let's say, minus q and minus q. Now this charge is now taken out of the picture and it is kept at infinity. So now this new F between them, this new force, since the distance is same, this will be 2q and minus q. So this is minus 2q square. So I can write is minus, so magnitude will be 2 divided by 4 into 4. This is my F dash and my F. So that is 1 by, let's say this is 2, so 1 by 8. So it is F by 8 is my correct answer. Now, a square surface of side L meter in the plane of the paper is placed in an uniform electric field voltmeter, and this, the horizontal side of the square is shown. along the same plane. This E is along the same plane. The electric flux linked to the surface in the units of voltmeter. Now see here, this square surface is placed on the plane of paper. Here there is no paper, this screen, in the plane of the screen, okay, and it is placed in a uniform electric field E that is acting along the same plane. This E is also along the same plane. This E is also along the same plane. This paper is also in the same plane. So I can directly say this answer is 0 because it is not cutting it. And you know that what is flux? Flux phi. Phi is E dot A. And what is the area vector? Area vector is always perpendicular to that of the plane, area plane. The plane is lying. So let's say this is dot. I mean, what does this dot means? Dot and cross dot means outside the paper. So it is making 90 degree. So E dot A, that is E and cos 90 degree, that is 0. 2 point dipoles of dipole moment P1 and P2 are at a distance x from each other, and P1 is parallel to P2. The force between the dipoles is. Okay, this is a direct question, I can say. This is my P1 vector. This is my P2 vector. Both are parallel to each other, and the distance between them is x. What is the force acting on them? So it will be 6 P1 P2 by x to the power 4. This is the direct question. Such questions also come so that you can directly answer them by the formula. Okay. The spatial distribution of electric field due to charges A and B is shown in the figure. Which one of the following statements is correct? A is positive and B is negative and mod A is greater than mod B. A is negative and B is positive and mod B, A is equal to mod B. Both are positive but A is greater than B. Both are negative and A is greater than B. Okay, let's see. See, from this A, the flux lines are coming out. So definitely A is positive, and from B it is actually entering. So B is negative. So this C and D are wrong. Now let's calculate. Let's count how many flux lines are coming out. Let's check A. From A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 lines are coming out, and from B, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, that is 10. So definitely mod of A, mod of QA, that is greater than mod of QB. So the charge, so my correct answer is A is positive, B is negative, and mod A is greater than B, mod B, since the more number of flux lines are being emitted. A small sphere carrying a charge Q is hanging in between two parallel plates by the same string of length L. Time period of the pendulum is T0. When the parallel plates are charged, the time period changes to T. What is the ratio T by T0 is given as? Okay, now let's see here. Time period is given by root over of 2 pi L by G. Here this 2 pi and root L that is constant, so this is actually time period is proportional to root over of G. Now let's see how the G varies when the electric field is launched. See, this is the bob and this is the thing, and what is the net force? The net force acting downwards, that is, one is mg. Other force, when since this is q plus q, since this plus q, electric field is from top to bottom like this. So that will be QE by m. So net force is QE by m plus mg. So the acceleration will be F by m. This is not QB by m, this is net force is QE, and if I have to find the acceleration, that will be F by m. So that will be QB by m by plus mg by m. Mm will cancel. That will be g dash. That is, I can write QE by m plus g. So I can write T by T naught. T by T naught will be g by g dash. This T corresponds to g dash and T naught corresponds to g. So that will be g by g. See this option, g by g plus QE by m and that whole root. So this is half, and that whole load is given. So option C is correct. A short electric dipole of dipole moment P is placed at the center at a distance r from the center of a solid metallic sphere of radius a, where a is greater than r. Okay, and the electric field intensity at the center of the sphere due to the induced charge on the sphere. Okay, this question is a bit interesting one. This is my sphere and this is a sphere. I'm connecting from the center to, let's draw a line here. Now this is R. This is R. See, due to this minus Q, there will be some minus Q charge will be induced here. Due to this plus Q, there should be some plus Q charge that is induced. This is minus Q dash, this is plus Q dash, and this center. And just let's see one thing. Now due to the, see, there is a dipole here. Dipole moment is, let's say, P. Now due to the dipole, the electric field intensity here, that is on the axis, that will be 2p by r cube and 1 by 4 pi epsilon naught. But the net electric field inside the conducting sphere should be 0. So to compensate the effect of dipole, these induced charges due to the dipole, that will add up and that will become 0. So this will generate an electric field in such a manner that this will compensate it. So E, I can write now, see, now this E will be 1 by 4 pi epsilon 2p by r cube. There are two options, one is along CO and another is along OC. Now let's see what happens here. See, the dipole moment is this side. The dipole moment is this side. So actually due to this Q, it will be the greater one will be acting this. The dipole moment is actually acting this side from minus to plus. So I can say electric field due to dipole will be ED will be this side. So to balance this, the electric field due to the induced charge should be along E, that should be along this side due to EI. So that is along CO. So my option B is correct. A semicircular arc of radius A is charged uniformly and the charge per unit length is lambda. The electric field at the center of the arc is, it is said semicircular. Now it is charged, uniform charge density is lambda per unit length. Now let's say at the center of the here, what is the electric field at this arc? Okay, I will do it by integration here. Let's say the charge is dq here, and let's say this is d theta and this is theta. Now due to this dq, the electric field here is dE. Electric field is dE and this is theta, and the component will get here, this is dE cos theta, and this d sin theta also will get, but due to some other electric field there, this d sin theta will cancel out. So we're only interested to find d cos theta. So that will, and just see what is dq. dq is this q by this total angular, that is say pi into d theta. So now what I can write here, there is integration, that is integration of d cos theta. What is d? d is 1 by 4 pi epsilon naught dq. dq is q by pi into d theta, dq by r square, r is constant, r square, dq by r square cos theta d theta, where I will be integrating it from minus pi by 4 to pi by 4. So let me take this out common. Now let me take this out common, and one more thing, this q by, let's add a r here, pi r, and let's add an r here also. This q by pi r, this will be my lambda, so it is given, so I will express in terms of lambda only, lambda by 4 pi epsilon naught, and r also will come out, and below it's r square, so it is cos theta d theta minus pi by 4 to pi by 4, and this r square and r, this one r will cancel, and my final answer that will come out to be my correct answer is here, option A, that is lambda by 2 pi epsilon naught A. Also we can do it by dimension arrays also, except for option A and C, and these are very trivial results, so it is very easy to answer. Okay, next, a hollow cylinder has a charge q coulomb within it. If phi is the electric flux in units of voltmeter associated with the curved surface B, then the flux linked with the plane surface A in units of voltmeter will be. Let's see here. This is the total flux due to all the surface, that is q by epsilon naught. It is q by epsilon naught. Now this I can write here, that is, let's say this is total flux phi t. Phi t will be flux due to the curved surfaces. There is 2 into the individual curved surface phi c, plus flux to the plane surfaces. There are 2 plane surfaces, so phi f, that means phi f, and flux due to the curved surface, that is given as phi only. The notation is given as phi. So now this becomes very simple. This phi t, that is q by epsilon naught, is equal to 2 phi f plus phi. So q by epsilon naught minus phi by 2. So my correct option is phi, option D, that is the flux linked with the plane surface A. That means only one surface it was asked. A point Q lies on the perpendicular bisector of an electrical dipole of dipole moment P. If the distance Q from the dipole is R, that is much larger than the dipole, then the electric field at Q is proportional to. See, this is a direct question again. This is a dipole, and it is asked on the perpendicular bisector of the electrical dipoles, this axis, that is the equator. Now the electric field will be something like this, that electric field, that is K P by R cube. So this will be option D. A solid sphere of radius r has a charge q distributed in its volume with a charge density rho is equal to k into r to the power a, where k and a are constants and r is the distance from the center. If the electric field at r is equal to r by 2 is 1 by 8 times at r is equal to r, then the value of a is 2, 3, 5 and 6. Okay, since the charge density is here not uniform, it depends on it is varying radially, as rho, it is varying radially, so we have to find out by integration. Let's apply Gauss law here. Let's take a Gaussian surface at a distance r, and see, Gauss law is integral of E dot ds, surface integral, closed integral of E dot ds is equal to q enclosed by epsilon naught. So q enclosed, what we can write, see, that is rho into dv. So how did I write dv is equal to 4 pi r square dr? See here, at a distance r I am taking a small elemental length dr, so the surface area is 4 pi r square and into this width. So if I can flatten out this, if I can flatten this out, this will be something like this. This width will be dr and this area will be 4 pi r square. So for rho into dv, what is rho? Rho I am replacing by k into ra. This q enclosed we cannot find out simply, we have to do integration. So 0 to r, k into r to the power a, 4 pi r square dr. So 4 pi k into 0 to r to the power a plus 2 into dr. 4 pi k divided by a plus 3 r to the power a plus 3, and this is my q enclosed. So I am putting this expression here. So integration of E dot ds, E is uniform at this Gaussian surface and constant, so I am taking out E. Integration of ds, that will simply give me, this is E ds cos theta because E is parallel to the ds vector. So that will give me 4 pi r square is equal to 4 pi k divided by a plus 3 into r to the power a plus 3. So this r to the power a plus 3 divided by r square will give me r to the power a plus 1. This is k by a plus 3. So this E, the value of E at r by 2 is 1 by 8 times value of E at r. So I am putting the relation here. So k by a by 3, a plus 3, here k by a plus 3, these two will cancel. This r by 2 to the power a plus 1, this r to the power a plus 1, and 1 by 8. So if r and r cancels, this r to the power a plus 1, it will cancel. 1 by 2 to the power a plus 1 is equal to 1 by 8. 2 to the power a plus 1 is equal to 8, a plus 1 is 3, and a is equal to 2. So my correct answer is a is equal to 2. Now, an electric dipole is placed along the x-axis at origin and at a point P that is situated at distance 20 cm from the origin such that OP makes an angle pi by 3 with the x-axis. If electric field at P makes an angle theta with the x-axis, then value of theta would be. See, let me draw it, it will be very clear. This is my P vector P, and this is my point. This is my point, and this is pi by 3 or 60 degree. And this distance is 20 centimeter, let's say r. And so at this point we have to find the electric field. So let's dissolve P into two components. This is my P cos theta, I'll show in different color. This is my P cos theta, and this is my P sin theta. For P cos theta, I will get a parallel electric field. For P sin theta, I will get an anti-parallel electric field. Let's say this is E1 and this is E2. And this E1 and E2 will have a resultant E, and the resultant is making an angle alpha with E1. So alpha and pi by 3, these two together, that will be my alpha plus pi by 3. That should be my answer. Now let's see what is alpha. I have already drawn this figure here. So this E1 will be 2p into cos pi by 3. Since this is parallel, this component is P, so this is parallel. So 2p cos pi by 3 divided by r cube into column this k, and this is E2. E2 is k into p sin pi by 3 by r cube, and if I divide them, tan alpha, that will be E2 by E1, that is half into tan pi by 3. This 2 will come below, this E2 by E1, so that is root 3 by 2. Tan pi by 3 is root 3 and root 3 by 2. So here I can write, so alpha is equal to tan inverse of root 3 by 2, and this will be my pi alpha and pi by 3. So alpha plus pi by 3, alpha plus tan inverse of root 3 by 2. So pi by 3 plus tan inverse of root 3 by 2. Sorry, pi by 3 plus tan inverse of root 3 by 2. So my option is option B. Now the last question, that is, a solid conducting sphere of radius 2a has a net positive charge 2q. A conducting spherical shell is of inner radius b and outer radius c is concentric with the solid sphere and it has a net charge q. The surface charge density on inner and the outer surface of the spherical shell would be. See, this is a question of charge distribution. Let me show you how to solve this. This is my inner sphere. This is my inner surface of the outer spherical shell and the outer surface of the inner spherical shell. Let me distinguish this by drawing the shades, and this is like this. See, the inner sphere has a charge of 2q. The outer sphere has a charge of minus q. Now, how will be the charge distribution? Due to this 2q inside, there will be a minus charge, negative charge that will be induced, that equal and opposite negative charge, that will be minus q. We have already discussed this in the previous questions, and there will be minus 2q and there will be plus 2q here due to this minus 2q. So in the outer surface of the outer sphere, the net charge I can calculate. The net charge is plus 2q minus q, that is plus q. and this one, this is minus 2q. So this is plus q and this is minus 2q, and this is b and the outer one is c. So now it is very simple. It will be minus 2q by this distance, that is 4 pi, this area, that is 4 pi b square. So minus 2q by 4 pi b square, this is my option A. This one is matching. The surface charge density on the inner surface of the spherical shell. Outer is only q is there. This is minus q and plus 2, plus q and minus q and plus 2q. That will be plus q by 4 pi c square. So option A is correct, matched. So that's all for this video, and if you like our content, then please subscribe to our channel and click on the bell icon, and please share this video with your friends so that everybody can be benefited. And please join our Telegram group for doubt discussion and practice questions. Thank you.